Okay, I'm going to do a short video on renal clearance. So, renal clearance is a measure of how effectively the kidney clears or removes a particular substance from the blood plasma. Right, so if we draw a very simplistic sketch of the glomerulus and the surrounding the attached nephron, make it look like this. Right, where this is the Bowman's capsule, this is the schematic nephron. We have the glomerular vessels come into Bowman's capsule. Right, and I've just drawn a single capillary loop here. It would be a much more complex capillary bed there, ball of capillaries for the glomerulus. So we have just to label things. So this is our inflow end. This would be the afferent arterial. This is our outflow end. This is the efferent arterial. This particular single capillary, although again it would be multiple, would be the glomerular capillaries, right? And again, this is Bowman's capsule and the nephron. So if we think about it, the volume of plasma which has the potential to be cleared of a substance by the kidney is the amount that enters collectively all of the afferent arterioles, right? We put the numbers on this relevant to, more than 2 million glomeruli and nephrons, even though I'm drawing it on a single one, right? So total, for all nephrons, we have about 625, again, just an average number, milliliters per minute of renal plasma flow. Right? So that's the amount of plasma that's flowing into both kidneys per minute. Now, the act of filtration is the act of pushing volume and solutes across the glomerular capillary wall, across the visceral layer of Bowman's capsule. That's actually the podocytes, not to get into the anatomy too much here, but it would be moving something from here into the nephron. Right? So from the blood plasma into the nephron. And it's easier to say what's not moved than what is moved, right? Because basically all of plasma content, not all of its volume, not all of the 625, but all of its content will readily move across except for the proteins. And again, since we're talking about plasma, we've already sort of left the cells out of the equation here because they don't have the potential to be filtered. In other words, 100% of the red cells come in here and come out over here. None of them are filtered. Same with white cells, same with platelets. None of them end up over here. They all just pass right through the kidney and are ignored. Plasma, all of it will move through, all of its contents will move through except for the proteins, right? So if the amount filtered here is about 20%, right? So GFR is 20% of renal plasma flow. It ends up being about 125 milliliters per minute. So that's 125 milliliters worth of glucose. The other 500 milliliters, 625 minus 125, right? The portion that wasn't filtered, all of the glucose in that 500 mils just went right on past, right? So it's almost like it's just taking 20% and shoving it into the nephron, right? And again, the only thing that's different is that the proteins all pass right through. They did not go through because the reflection coefficient of the glomerular capillaries is such that we don't filter proteins. Everything else goes through. Nutrients, wastes, electrolytes, water. Okay? Now, if we were to excrete everything we filtered, right? So put some dots here to represent our a particular filtered solute, right? For this first scenario, we're going to talk about a substance that is filtered only, and then the nephron doesn't do anything with it. It just ignores it, right? It doesn't reabsorb it, doesn't secrete it. So in that scenario, what is filtered would be the same amount that is excreted. In other words, if we filter 125 mils per minute worth of creatinine, then we will excrete 125 milliliters per minute worth of creatinine. In other words, its clearance, the volume of plasma cleared, would be the 125 mils that are filtered per minute. Right? That's why creatinine and inulin, an exogenous molecule, you have to inject it into the body, handled the exact same way as creatinine, not reabsorbed or secreted. That's why the clearance of those substances equals GFR, right? Because if you actually calculate, there's a way to measure urine and plasma content and volumes and things to get the clearance, and if you do that, you will actually get the measure of GFR, because again, whatever you filter, the volume you filter is the volume you would excrete, right? I should say the amount of creatinine in 125 mils per minute would be excreted, right? You're clearing 125 mils of plasma of the 625 that came in. All right, so that's no reabsorption or secretion. Now let's say we're going to filter another solute. Let's pick glucose, right? Well, let's not pick glucose. Let's pick, I can give that example in a minute, but let's do sodium, right? Well, sodium is dramatically reabsorbed. Reabsorption is the process of taking something that was filtered and putting it back into the bloodstream. So it's going to actually go back into, right? These are the peritubular capillaries, right? And so if we reabsorb something, so let's take some of what this filtered quantity of sodium, and we're going to take it, we're going to move it to here. We're going to reabsorb it into the interstitium, and then the peritubular capillaries reabsorb, right? The Starling forces there favor reabsorption all the time. So we're going to move it from here into here. So what's going to happen to our amount that is then excreted? It won't look like this anymore. It'll look like that, right? We remove, right, several, I'll put a couple more here, remove several of these, and there will be less left over here. Therefore, when you reabsorb, you excrete less than you filter by the amount you reabsorbed, right? You're excreting this amount, right, which is less than this amount, the filtered amount, by the amount you reabsorbed. And if you think about it, that means we're clearing a smaller volume than what was filtered. Right? We filtered 125 mils per minute worth of sodium, but we didn't excrete 125 mils per minute worth of sodium. It was some much smaller amount. For the electrolytes, very small. Right? And so the clearance of reabsorbed solutes is significantly less than 125. Sodium, in fact, the clearance of sodium is less than 1. It's like 0.9. Chloride is like 1.2. Other electrolytes, a little bit higher than that, but still very low, right? In other words, dramatic reabsorption. Okay? So, again, the clearance of a substance that is reabsorbed is less than what is filtered, right? And the amount is less than what is filtered is the amount that's being reabsorbed, right? This is subtracted from what's filtered to give us what's excreted, right? Clearance goes down. Now, if we change our picture here a little bit, right? Instead of reabsorbing a solute, we're now going to pick a solute that we're going to secrete. And so now, in this scenario, we're going to take a substance from here, and we're going to transport it into the nephron. We didn't do anything with the filtered load. The filtered load of this solute is already here, right? This is going to be a waste product. And you'll see why that makes sense in a minute. But so the filtered wastes are already here. We're going to secrete, right? This is secretion, from the interstitium into here. So now we're adding to what was filtered, right? So the amount that's excreted will be what is filtered plus what's secreted. The amount excreted will be the amount filtered plus what's secreted. So I have to add a few over here. Right? And so our excretion goes up, but our clearance goes up too, because now we are clearing not only what was filtered, but at least a portion of what was unfiltered. So we cleared the 125 mils a minute, that was this, right? But we're clearing some fraction, maybe the whole fraction, the content of the 500 mils per minute that went here, right? There was the unfiltered plasma volume. And so the clearance of a secreted substance, always a waste, is higher than what's filtered by the amount that's secreted. Higher than what's filtered by the amount that's secreted. So it's this plus this to equal this. Right? And so again, so now we're going to have a clearance value that's significantly above 125. Because remember, filtered alone would give you 125. So now we're going above that. Now the maximum we could get to would be clearing everything that's filtered, 125, plus what was unfiltered, 500, which is the 625 we had coming in down here. In other words, you could clear everything. The only substance that's really handled that way is called PAH, para-aminohippuric acid. And it is secreted 100%. In other words, all of the 500 mils that gets per minute that gets to here has its pH removed from it. So think about that. That means that the renal vein, the blood leaving the kidneys, has a pH concentration of 0, meaning the kidneys cleared all of the plasma flow of that substance. And so the clearance of PAH equals renal plasma flow. Right? Now, there is the possibility of saturating transporters. Okay, so now let's give you one last example here. Right? We're going to go switch back to a reabsorbed substance. Right, so I have to change my arrows, right? The secretion is in, reabsorption is out. Clean this up a little bit. Okay, so we have our filtered load here. Now we're gonna talk about glucose, right? And so here comes 20% of the glucose, right? That's the filtered fraction. 80% of the glucose passed right through. 80% of everything passes right through, right? 100% of the proteins, but everything else, 80%, right? Because 20% goes here. Now we said it's a nutrient, right? We do not want to be excreting nutrients, so they're going to be reabsorbed. So we're going to do this, right? Which means, and for a nutrient, we really want this amount that's being reabsorbed here, this is reabsorption, to equal the amount that's being filtered, such that, right, the amount that we're going to excrete over here is 0, right? The clearance will be 0, right? In other words, we take all of these, and here they go. Just reabsorb them all. There they are. They end up going into the bloodstream. They've been saved. The kidney does not excrete them. However, there is a point at which the transporters, molecules that are aiding the movement of glucose, or any other solutes, or most other solutes at least, out of the nephron can become saturated. What that means is that you provide them with so much glucose, right? If our blood glucose levels rise, then the filtered concentration of glucose rises. It starts to look like this, right? More and more glucose would get filtered. Now, within a normal range, the transporters keep up, and right now we just have to add more and more up here. Right? Transporters are keeping up. We just keep moving it in the bloodstream. Pathologically, in type 2 diabetics, when blood sugar levels can go to sort of crazy high levels, much higher than normal, then we can add so much glucose here. You'd add some more here, but then all of a sudden, some of them get passed. Right? You've reached the transport maximum. You can't transport transport continues, it's running maximally, but now you've added so much here that it can't get it all out, and some of it will end up getting past the transporters, which means it gets excreted, which means the clearance of this particular nutrient, glucose in this case, is no longer 0, right? Because we are now clearing some small fraction of the glucose from the plasma. You can't say its clearance is 0 if you're actually excreting it, because clearance is actually excretion relative to the plasma content, right? And so, again, if your numerator is not 0, then your answer is not 0. And so, again, we start to clear some of the plasma of glucose. Now, it's not much at that point, but it does mean it's non-zero anymore, right? And so, again, the point here being our transporters generally keep up, right? And our clearance matches the sort of the relationship between filtration and reabsorption, or filtration and secretion, the previous picture, until, and it breaks down slightly when we reach the transport maximum, and then you don't keep up with, in this case, the reabsorption relative to the plasma content, the amount that's being filtered, and some gets excreted. Okay, that's clearance, right? We end up with a scale, right? Don't forget our scale. It shows us sort of like the benchmarks of 0, 125, and 625, right? 0 is what we were just talking about, so this is clearance. The units are what I said before. It's always in milliliters per minute because that's the rate of plasma flow that we have the potential to clear, right? So you're going to clear some fraction of it. You're going to clear 0 mils of that 625 or something greater than that. Nutrients would be down here at 0. The only thing way up here at 625 was that substance PAH that I talked about, right? Where you filter a portion of it, and then everything you didn't filter gets shoved in here anyway, right? What that means is you get, and my letters here indicate the magnitude of the process, right? So above 125, which is filtered only, F only, right? Filtered only at 125, and then it's a little bit of secretion, more, a lot, tons, right? The same thing holds true, but in the opposite direction. When we go south of 125, we go less than 125, it means we're removing it, and we're clearing less than 125, and so it would be reabsorption, reabsorption, and reabsorption, right? And again, maximal getting us down to 0, in which case there's no excretion whatsoever. All right, one of the things you want to be able to do is determine how a particular solute is handled based upon the value of its clearance. That's why the 0, the 125, and the 625 are such important benchmarks, right? Because they really kind of give you the extremes. Completely reabsorbed, not reabsorbed or secreted, and completely secreted. All right, hope that helped.